Eigenvalues and eigenvectors are fundamental concepts in linear algebra. For a square matrix A, a non-zero vector versus is called an eigenvector if multiplying A by versus only scales the vector by some factor lambda. This is captured by the equation A times versus equals lambda times V, where lambda is the eigenvalue associated with eigenvector versus. Let me illustrate this with a visual analogy. Imagine you have a special stretchy sheet. When you stretch it, most lines on it change direction. But some special lines only get longer or shorter, keeping their original direction. Eigenvectors are like those special lines. And eigenvalues tell us how much they stretched or shrunk. In our example, the red and green lines were eigenvectors. The red line stretched by a factor of 2. So its eigenvalue was 2. The green line shrank by half. So its eigenvalue was 0.5. In math, especially linear algebra, we use matrices to describe transformations like stretching, squeezing, or rotating things. Let's take this matrix, A, as an example. Watch what happens when we apply matrix A to the standard basis vectors and another vector x. Their directions and lengths change. Now, let's look at a general vector, x. When we apply matrix A, it transforms to x, changing direction. But watch this special vector, v1. When we apply A, it becomes av1. Notice how av1 points in the exact same direction as v1. It only got scaled, stretched. In this case, this special vector v1 is called an eigenvector of A. The amount by which the eigenvector is scaled is called the eigenvalue. Here, the eigenvalue is 3, because av1 is 3 times as long as v1. This relationship is captured by the famous equation, A times versus equals lambda times versus, where A is the transformation matrix. V is the eigenvector, the special direction, and lambda is the eigenvalue, the scaling factor. Let's see our matrix A transform space again. We have our two eigenvectors, v1 and v2, and another vector x. Watch what happens when we apply the transformation A. See, the white vector x changed direction completely. But the yellow eigenvector v1 only stretched along its original line by a factor of 3. Its eigenvalue. And the teal eigenvector v2 also stayed on its line, scaled by a factor of 1. Its eigenvalue, meaning it didn't change. Eigenvalues and eigenvectors might seem abstract, but they are incredibly important and appear in many real-world applications. In data science, Principal Component Analysis or PCA uses eigenvectors to find the most important directions in complex datasets, helping to simplify data while keeping the most information. Engineers use them to analyze structures like bridges, finding the frequencies at which they might vibrate due to forces like wind or earthquakes. These natural frequencies are related to eigenvalues. In quantum mechanics, eigenvalues represent measurable quantities like energy levels of an atom. The state of the system is described by eigenvectors, called eigenstates. Even Google's original PageRank algorithm, which ranks websites, relied heavily on finding the principal eigenvector of a massive matrix representing the links. between web pages. The corresponding eigenvalue is 1. So, eigenvectors and eigenvalues give us deep insights into linear transformations, revealing the stable directions and scaling factors hidden within matrices. They are fundamental tools across science and engineering. I hope you found this video helpful. If you enjoyed it, please give it a thumbs up, subscribe to the channel, leave a comment, and share it with your friends. Your support means a lot. See you in the next video.